All right, so lecture 11 was about generic rigidity of linkages. So we've got bars and vertices connected together in a graph. And generically, the graph is all that matters. And we characterize in two ways, Henneberg construction and Demaine, when graphs are generically rigid. And in particular, there was this pebble algorithm that was supposed to tell you in polynomial time whether your graph is Demaine or not. And everyone pretty much asked about this, about the details, including myself. When I watched it, I was like, that seems a little sketchy. So I thought I'd spend most of today going through how that algorithm works exactly, and also why it's correct, which is definitely not obvious. It kind of vaguely feels correct, but we'll see why it actually is. Remember Lemaine's theorem. The Demaine characterization is that your graph is generically rigid if and only if every subgraph, let's say every k vertices induces at most 2k minus 3 edges. That's part one, and you also need that the number of edges overall in the graph is 2n minus 3, where n is the total number of vertices. So this was just the degree of freedom count. You have 2n degrees of freedom for every vertex, minus 3 for the rigid motions, 2 translations, 1 rotation. So that's the number of edges you should have total. And then, this is for minimally generically rigid. And then to make it balanced, you want to guarantee that every k vertices doesn't have too many edges. Because if it had too many edges, there'd be too few somewhere else. This part would be overbraced, some other part would be underbraced, and you'd be flexible. That's the intuition. And so the tricky part comes down to how do you check whether every k vertices induces 2k minus 3 edges? Because there are exponentially many choices. There's 2 to the n different choices of subsets of vertices. For each of them, you'd have to check. That's no good. So the algorithm wants to check this. And I'm going to call this property the 2k minus 3 property. And we're going to warm up with a simpler problem, which is to check the 2k property without the minus 3. So 2k property is just every k vertices induce at most 2k edges. So this will be a little easier to think about, more or less the same, a lot easier to argue about. And then we'll see how to modify the algorithm to check the 2k minus 3 property. Was the property clear? And in particular, inducing. Inducing means that you have some set of vertices, and there's the rest of the vertices, n minus k of them. You only look at edges where both endpoints are in the set. Both of them are among the k vertices. So you ignore vertices that have one end in k and the other end outside, and you ignore, obviously, edges that have both ends outside. Just count these guys. Okay, so how do we do this? Let me give you the algorithm. Actually, let me first give you the idea of the algorithm before we go to the actual algorithm. And this is sort of review, but pretty soon we'll get to stuff that wasn't covered in lecture. So the idea is every vertex has 2 pebbles inside of it, which I'll draw as 2 red dots. And they can cover incident edges. So they can't move very far. They have to stay basically inside or on the boundary of the vertex. That's how I'm going to draw it. Each pebble can cover one incident edge. So for example, here's a little graph. I could take, maybe I leave one of the pebbles in the middle. I can move one of the pebbles to cover one of the edges. So I'll put it at this intersection to denote it's covering this edge, but it still belongs to this vertex. Pebbles cannot change vertices. They have to stay kind of local. These two pebbles could just stay where they are. Here we could put one pebble here, another pebble there, one pebble here, one pebble here. This is what I call a pebble cover because every edge is covered by some pebble. And that's sort of the goal in a pebble cover is to cover every edge. You only need to cover it once. And the pebbles can either cover an edge or they can be free. I'll call them free if they're just hanging out in the inside here, not being used for anything. Okay, so our goal is to find pebble covers. But the first claim, why do I care about pebble covers? I claim that having a pebble cover is equivalent to the 2K property. So that's what I want to show. So let's start with that. This is sort of why everything is working. A graph has the 2K property if and only if it has a pebble cover. So that's why we care about these pebble coverings. This is actually pretty easy to prove and gives a lot of intuition for why everything works here. So let's start with the left direction. So suppose I have a pebble cover. Suppose somehow I've achieved this property of covering all the edges using only 2 pebbles per vertex. I claim that we then satisfy the 2K property. 2K property says you take any K vertices, you induce at most 2 K edges. So let's consider K vertices. If someone chooses K vertices, it doesn't matter which. This should hold for all of them, for all choices. So we've got, K vertices here, n minus K vertices remaining. We claim that the number of edges induced by those K vertices is at most 2K. So look at one of these edges that's wholly inside, that's induced by these K vertices. I claim, well, that edge must be covered by a pebble. Which pebble? Well, either this one or one on the other side. But the point is it is covered by a pebble among these vertices. So my concern is, well, maybe you worry about an edge like this. It has, or maybe, you worry about a pebble here that's covering this edge. But that edge is not one of the induced edges. So these vertices are irrelevant. It's just the pebbles inside, just among these 2K pebbles. So in here there are 2K pebbles. They must fully cover the induced subgraph. They must cover all the edges in here. That means there are at most 2K edges, because there's one pebble per edge at least. Okay, so there's 2K pebbles in here. This means there are at most 2K induced edges. Clear? That's sort of the obvious direction. This doesn't really exploit very much about pebbles. The other direction is a little more interesting. Why should these pebble covers exist? Because they seem pretty constrained. Pebbles can't move very far. It's not really clearly the same, but it is. So if we have the 2K property, so now we know that every subgraph of K vertices induces at most 2K edges. Now we want to prove that a pebble cover exists. This, I'm going to wait. Okay, it will become obvious momentarily. This is kind of fun. Sometimes it's easier to prove a theorem than it is to come up with an algorithm, but in this case it's easier to come up with an algorithm than it is to prove the theorem. And you can use the algorithm itself to prove the theorem. So I'm going to prove this in a moment. Stay tuned. Meanwhile, we have an algorithm. This algorithm is an example of what we call an incremental style algorithm, where you imagine starting with the empty graph, and then you put in all the edges that belong one at a time. So add edges one at a time, starting from nothing. One detail is we're going to imagine as edges get added, we want to direct them. We're going to direct edges from the pebble that covers them to the other side. So if we have an edge and we have a pebble over here, then I'm going to imagine the edge is being directed from the pebble to the other side. That's just for convenience for expressing the algorithm in a moment. Okay, so now, so this is for the 2k property. We'll get to an algorithm for 2k minus 3 in a little bit. So now we have a for loop over the edges we're going to add. And when I immediately add an edge, it will not be covered. So it's sort of not directed. It's just some edge, VW. I would like to put a pebble here, but it could be both pebbles at W are occupied for some other edges. It could be some, the pebbles for V are also occupied for some other edges. And that would be annoying. I want to somehow reassign a pebble to cover this edge. So what I'm going to do inside this for loop is search for available pebbles. And in this case, what turns out to be right is a directed path in this directed graph from either V or W to a free pebble. So either I find one or I don't. If I find one, let's say from V, there's some edge, and then some other edge, and then some other edge. And eventually I find a free pebble. Remember, a free pebble is one that's floating on the inside, not being used for anything. So what does my picture look like? Remember, edges are directed from the pebble. So that means there was a pebble at V being used for that edge. There's a pebble at this vertex being used for that edge. There's a pebble at this vertex being used for that edge. In this case, what do I do?
Reverse them.
Reverse them, yeah. Just reverse all the edges. So I had this edge VW here. I wanted to put a pebble here, so I'm going to reassign this guy to be over there, this guy to be over there, this guy to be over there, and so on. So I end up with, it's kind of in the way. Put W over here. The new picture is I have V and W. I'm going to have leftward directed edges. So now this pebble got assigned to be here. I can't draw left apparently. The other left. This pebble is assigned there. This pebble, the free pebble gets used up. And now we've got a free pebble over here. And now we can assign it to be on the edge VW. So if I can find such a path from V or from W, I'm happy, because then I can reassign. Okay, so if I find such a path, I just shift the pebbles like that, and I'm done. But what if I can't? This is the critical issue, and it is also core to this part of the proof that we haven't yet done. why would we hope for pebble covers to exist in the first place? We don't know. I claim if this algorithm fails to find a path in this situation, then you can immediately say you do not satisfy the 2K property. I'd like to say there's no pebble cover, but that's a little harder. I'm going to say you do not satisfy the 2K property. And we actually know already from this part, pebble cover implies 2K property. The contrapositive, which we've already proved, is if you do not satisfy the 2K property, you do not have a pebble cover. So that will actually guarantee correctness of the algorithm if I can prove this part, that it violates the 2K property. Then I'll know there was no pebble cover and I'm done. Okay. So why is this true? I claim if you look at all the nodes reachable by directed paths from V and W, then that is a set of nodes that induce more than 2K edges. So let's say there are K nodes that you can reach. I claim there will be more than 2K edges among them. Why? It's fun to have proof in the middle of an algorithm. So here we've got V and W, and these are the K nodes that are reachable from V and W, which means all of the other edges are pointing into this set. And then over here we have everybody else. I mean, it might be everyone, but potentially there's some vertices over here. All the edges are directed from right to left. Otherwise, we could reach more stuff. Okay, so what's the situation? VW is uncovered. There's no pebbles that cover it. These edges, every other edge is covered because there's only one uncovered edge at any moment. These edges are all covered from this end. That's what these directions mean. Which means all the pebbles in here are used to cover induced edges. So all the pebbles in here are covering induced edges, and yet there's one induced edge that is not covered. Now they're exactly 2K pebbles. They're all being used. I'm assuming here you never have two pebbles covering the same edge. So that means, so there's 2K pebbles. They're all used to cover induced edges, which implies you have exactly 2K plus 1 edges. Plus 1 is VW. So that means the graph that we've created so far violates the 2K property. Now we haven't added all the edges yet, but if we add more edges, it's going to get even worse potentially. If we have 2K plus 1 edges now, in the actual graph we'll have at least 2K plus 1 edges. So if this search fails, you know that you violate the 2K property, which means you know that there's no pebble cover. So that proves correctness of the algorithm. Now we can come back to this claim. This follows by correctness of the algorithm. Okay, why? We want to prove if you have the 2K property, then you have a pebble cover. Well, if I have the 2K property, this algorithm will work. This case can never happen because it can only happen when you violate the 2K property. So if you have the 2K property, this algorithm, you can keep running it. You'll always find a path. It'll be able to shift the pebbles and always cover things. And so you get a pebble cover from the algorithm. The end. So that's how you argue that if you have the 2K property, you get a pebble cover. And it's kind of nifty. Without this algorithm, this would be quite tricky to specify. But the algorithm tells you where the violation would be, tells you where you would violate the 2K property, and that lets you prove the claim, ultimately. Any questions about that? This, I think, is kind of the heart of pebble algorithms and why they work. It's the cleanest part. It gets a little bit messier to do the 2K minus 3 thing, so we'll move to that next. Maybe before we go there, we can talk about the running time in the algorithm. For those so inclined. So the heart of the algorithm is this step: search for a directed path from V or W to a free pebble. This is essentially some of the nodes have free pebbles. Those are like good nodes. But basically, we've got a directed graph. We want to find all of the nodes that are reachable from V. See if there's any good nodes that have free pebbles. Search from all the nodes. W. This you can do with a depth first search or a breadth first search or your favorite search algorithm. It takes linear time. Order the number of vertices plus the number of edges in the graph. We do this search V times. Why V times? Well, actually why V times? So we add edges one at a time. We're hoping that we have the 2K property. The 2K property implies that in particular there are at most 2V edges. So in general we do this E times. We keep adding edges. We would add E edges to the graph, hopefully. In general, E can be much larger than V. In a graph, E could be V squared, in the worst case. But this algorithm will fail by the time you add 2K plus 1 edges, because then you definitely don't satisfy the 2K property over the entire graph. So in particular, you won't satisfy it on some subset of vertices. So you only have to run this loop V times, not E times, or 2V times. So this is a little bit smaller. And so this product is V squared plus VE. Normally we write VE, but this is slightly more precise, which is the same as Bellman-Ford algorithm if you've taken algorithms. I'll just mention that there is an algorithm slightly fancier that just requires this term. So this is possible. You don't need this VE part, but it's kind of beside the point to our goal, which is just to understand when things are rigid, when they're not, in an efficient amount of time. So this is polynomial in any case. This is also the best known algorithm, V squared. Open problem is whether you can do better. All right. Questions? Yeah.
If there are more than 2V edges, is that a problem? Isn't that automatically a problem?
Yeah, if there are more than 2V edges. Oh, right. So there's done. Great. You can just check in the beginning, are there more than 2V edges? If so, you do not satisfy the 2K property. And so you can stop. So that takes constant time to check those cases. And otherwise, E is small. And then you only take V squared time. Thanks. That's cute. All right. So that was the 2K property. Let's do 2K minus 3. For the 2K minus 3 algorithm, it's going to be pretty much the same as this algorithm. So in particular, every vertex has to attach pebbles. Each pebble can cover one incident edge, otherwise it's free. Our goal is to cover every edge. But it's slightly different. We have to deal with this minus 3 business. And for that, we need another claim. Which is that a graph has a 2K minus 3 property if and only if G plus 3 copies of an edge E has the 2K property for every edge E in G. I should probably say G has. So I want to know whether ultimately I care whether my graph has a 2K minus 3 property. This is most of the Lemon condition. It's the hard part to check. And 2K property is what I know how to check. So I claim all you need to do to check it, this would actually be an algorithm, is for every edge, turn that single edge into 4 copies of the edge, add 3 more, check whether it has a 2K property. Remove those extra 3 copies, take the next edge, add 3 copies, check the 2K property. So with another factor of e, which has to be order v. So if you're willing to spend v cubed time, you can just run this algorithm for each edge, quadruple it, see whether it still has the 2k property. Okay, so that's the connection between these two things. Let me prove this claim, and then I'll tell you a better algorithm that only takes v squared time. So, proof. Which one's easier? In both cases, I want to take k vertices. And then I'll do this direction first. Okay, so how do we prove this? First, this is actually really easy. Suppose G has a 2k minus 3 property. So if I have k vertices here, I know that the number of edges in here is at most 2k minus 3. So here's k vertices. Looking at the number of induced edges, it's going to be at most 2k minus 3. What I'm claiming is then if I quadruple an edge, if I add 3 new edges, I have at most 2k edges afterwards. I think that's pretty clear. 2k minus 3 before at most. If I add 3 copies of any edge, could be in this set or outside the set would be even better. The number of edges inside the set will be at most 2k. So this is in G. This implies there's at most 2k in G plus thrice E. Okay, this is non-standard notation, by the way. It just means add 3 copies of that edge. So we'd normally draw that like this. 4 copies of the edge. Okay, so that was half of the claim. Pretty trivial. The other half is almost as trivial. So in the other direction, we assume that G plus 3E has this property for every edge. And now we need to prove that G has a 2k minus 3 property for every set of k vertices. So we're looking at that set of k vertices. We want to argue that in G, there's at most 2k minus 3 edges. What we know is that in here, in G plus 3E for any E, so it's a little awkward. So let me start by drawing G. We want to claim that the number of edges in here is at most 2k minus 3, so I'll put a question mark. So there are 2 possibilities here. It could be either this graph is completely empty. If there are no edges in here, then surely there are at most 2k minus 3 of them, assuming k is bigger than 1. Okay, which I haven't mentioned, but throughout here I need that k is bigger than 1. You can never have -1 edges on a subgraph. So the 2k and the 2k minus 3 property only hold for at least 2 vertices. K is at least 2. Okay, so if there are no edges, fine, I'm done. If there are edges in here, then I can do this trick. So there's some edge. Pick your favorite edge, call it E, in this subset. Produce out of it G plus 3E, which just looks like the same thing, but now it's got 4 copies of that edge. This we know has at most 2k edges in here. The original graph is exactly the same, except it lacks those 3 edges. Therefore, there's at most 2k minus 3 of them. Done. So it's really the same kind of proof in both directions. Just here, you have to use your freedom in choosing E to choose an edge that is induced in this subgraph. You can't choose some other edge out here. Okay, question?
So this seems kind of cheap because we're using the graph as a linkage.
Okay.
In the end, so sort of like adding these extra edges, they all sort of collapse into one.
Interesting. Right. So why this feels like cheating because from a linkage perspective, these 2 guys have exactly the same constraints.
Yeah.
I agree. It's weird. At this point, this is a device. You can think of it as adding edges. Another way to think of it is this edge has to be covered by 4 pebbles. That's probably a little more intuitive. So having to cover an edge by 4 pebbles essentially is pinning the edge, because on the one hand you have a single pebble just to say, okay, this is an edge. And then you have 3 more pebbles to eat up the translations and rotations. That's intuitively what's going on. I agree this looks weird. And at this point, we're just playing the graph theory game and ignoring the linkages. That's the short answer why this is okay. But ultimately, intuitively, what's going on is that these three edges are just representing the translations and rotations being eaten. And they have to be somehow eatable universally at every edge. That's what this is saying. I don't have a great intuition for that, but it is pretty sure you do need to say for every edge, not just some edge. All right. So at this point, you have a polynomial time algorithm, so I'm kind of done. But let me briefly mention how you can make it faster by modifying this algorithm to do the 2k minus 3 situation. Dare I won't literally modify the algorithm. I'll write it a new version, but I'm going to use that as a subroutine, basically. Okay, so algorithm 2k minus 3 version. So it's going to be the same style. We're going to add edges one at a time. We'll direct the edges in the same way for each added edge VW. So I'll just write for each added edge VW. Before, I just tried to add the edge and cover it with pebble. Now I want to cover it with 4 pebbles. I want to basically add the edge 4 times. I'm going to write as above to mean this step. So every time I add the edge, I search for a directed path from V or W for a free pebble. When I find it, I do the pebble shift. I do that 4 times. Then basically I have 4 pebbles on the edge, or you can think of them as being 4 copies of the edge. Each has 1 pebble. Either I succeed and I get all 4, or I don't get all 4. Okay. On success, at that point, this was just a temporary measure. At that point, I'm going to delete 3 of the copies, put it back to a regular single edge. This frees 3 pebbles for future use. So I don't want every edge to be quadrupled. I just want, I don't want them all to be quadrupled at once. I want to try quadrupling one edge, then try quadrupling the next edge, try quadrupling the next edge. But when I'm quadrupling an edge, all the other edges exist as single edges. So I delete the 3 copies, and then this for loop continues and tries the next edge. On failure, here I'm going to say something more interesting. Normally on failure I'd say, well, you don't satisfy the 2k minus 3 property, game over. But you can be a little more sophisticated. Just say delete all the copies of E. I guess there's 4 of them. Whatever pebbles you could acquire, you give them up. Delete the edge, and call the edge redundant. Basically, in this case, you can argue that edge was superfluous for rigidity purposes. You didn't need it. So the algorithm doesn't just fail, it says this was a useless edge. And it'll tell you which edges are useful, which ones are non-redundant from a rigidity standpoint. And then when you're done, you will be rigid if and only if the number of non-redundant edges that remain equals 2n minus 3. So that's sort of the last part of the Lemon check. So this is giving you a little bit more information than just, do I satisfy the 2k minus 3 property? To get that, you just check whether you ever failed. But in this case, you can actually see, these are the useless edges. They're kind of, those are the overbracing edges. Everything else is useful, and if I end up having enough useful edges, 2n minus 3 of them, then I know I'm rigid, otherwise I'm going to be flexible. So this gives you all the information you want. With a little bit more effort, you can even figure out if I'm flexible, which parts are rigid and which parts can move relative to each other. This, of course, generically rigid. Okay, finally, let me show you this thing in action. So look over there. This is an implementation by Audrey Lee St. John. And so here's a simple graph. You can probably see this top part is flexible. It's quadrilateral. Bottom part is overbraced. This is in 2 dimensions, right? So just triangles would be enough, but I've added an extra edge here. And this is going to check the Lamont condition one step at a time. So we start with 2 pebbles everywhere. We start by adding that top edge. Right now there are 4 pebbles on that edge, so it's great. I can just add the edge. Let's say I added it 4 times. There are 4 pebbles there, but then in the end I just need 1. So it's skip that step, and now I've got the 1 pebble from B, and we're happy. Okay, so that is its own rigid component. Next, let's add this edge EF. So this also has 4 pebbles on it, so we're done. Next we have CD. That also has, you can change the order if you think this one's a little trivial. Now is when the action happens. Let's add this edge BC. So currently it is only covered by 3 pebbles, but we need a 4th. So we're going to take one of these free pebbles on A and move it along B. We found that by starting from B and searching out and finding a free pebble. So we just flip that edge. Now we've got a free pebble on B. Now we've got 4 pebbles on BC, and we can add the edge. Okay, but we only actually take 1 of them. So I'm kind of skipping the part where we add the 4 copies and immediately remove 3 of them, because that's kind of silly. Cool, so that's its own rigid component, it turns out. Each of these things is independently, the colors represent rigid components. And right now, nothing is tied together. Everything's flexible. Flexible at B, flexible at C. Okay, let's add this diagonal, DF. So right now it only has 1 pebble, which means we need 4 pebbles. So we're actually gonna have to get one at F. We're gonna have to get one at D because there can only be 2 at each. So first we'll do, I guess, a search from D, and we immediately find a pebble. We move it down there. Great. Then we search from F. We find a pebble there. We move it. Boom. We've got our edge at all 4 pebbles. Okay. Eventually we're going to run out of pebbles, but right now we're very flexible. Okay, let's add this other diagonal. This should also be possible. Right now there's 1 pebble at E, 1 pebble at C. We've got to find 2 more pebbles. So first we'll follow this edge, find a free pebble at F. That was easy. Next we'll look at from C. There's only one way we can go from C. We can't follow the back edge. Got to go forward. Got a pebble at D. We flip it around. Now we've got 4 pebbles on C and E, so we can add the edge. Okay, let's add EF. Right now we've only got 1 pebble, yet we need 4. So let's start by searching from A. Oh, we found a pebble immediately. In general, we'll have to follow many edges. So there's A. From F, there were 2 ways we could go. Either one of them would have given us a pebble. Let's flip the yellow edge. Boom, we've got F. 1 pebble, but we need another one. Now we cannot get another pebble from E because we just flipped the edge, but we can get a pebble from D. So we flip that edge, and now we can add the edge AF. 2 more edges. That's a little tedious. So next is CF. Running out of pebbles here. There's only like 5 pebbles total in the system. We need 4 of them right here, so because we're getting almost rigid. So let's see. We've got CF. Let's start from searching from F. There's only one way we can go. We find a pebble. We flip it around. Now we've got C. C. There's only one way to go from C. We find the pebble at E, and we flip it around. Now we've got the 2 pebbles. Cool. So we've got the 3 pebbles here, which are representing our translations and rotations. The only other pebble left is this one, which is basically representing the degree of freedom in this quadrilateral. So when we go to add the last edge, which is, so at this point this is a rigid component because of the triangles. When we go to add the last edge, we will fail to find enough pebbles. Let's see. We can find 3 of them. We can grab the one from E, or let's see. So, all right, it's not going to show us. But from E, we can grab F, the pebble at F. From D, we can grab the pebble at C. From D, we can grab the other pebble at F. We've got 3 pebbles, but there's no way to get to this pebble because both of these edges are directed down, So you can never get from the below part to the above part. So it's not obvious that this is working. That's what the proof was for. But at least you see it in action. I'll just run it very quickly for another graph. Let's say a big one. This one is minimally generically rigid. So it's kind of fun to watch for a while. You get pebbles moving around. In this case, you have some longer paths you have to follow to get enough pebbles. It depends a lot on the insertion order that you use. So, but in each case, you need 4 pebbles, 2 on each side. And if so, you can add your edge. Otherwise, you can't. What I haven't described is this color coding, which is figuring out when you have rigid components. Roughly speaking, to find what your rigid component is, if you're an edge, you want to know what rigid component am I in. You basically just search for all the vertices that are reachable from your edge. Those are all in your rigid component. That's sort of what we saw. So this graph happens to be minimally rigid, and it detects that. But then it can be a little bit more as in your rigid component. Some of the incoming edges, let's see, draw a picture. So here's everything you can reach from VW. And say you're following an incoming edge here from some other vertex U. And then suppose these are all the things that you can reach from U. If there are 0 pebbles out here, then this whole thing is a rigid component. And you just keep doing that. You check an incoming edge. If there's 0 pebbles in that reachable piece, then you merge. And you keep doing that. Those are all the things that are rigidly attached to you. So I won't prove that. It's a little tricky to prove. But it's fairly easy to compute. And you can actually do it in the same amount of time. As you're building this thing up, you can do the color coding to figure out which things are in the same component, which things are in different components. Let's see. So another fun fact is this little part. This says it's the 2k minus 3 property. The same algorithm you can use to check 5k minus 27 or whatever you want for fixed numbers like 2 and 3. The same pebble algorithm can detect that ak minus b property. And that's actually useful for a lot of different things. This was done originally by Lee and Stranu, same Lee. And Stranu will be seeing some of her results in a couple of classes as well. For example, so this is that. 3D body and bar. So actually let me show you the kind of scenario we're thinking about. So I mentioned 3D, if we have vertices and bars between them, we don't know how to characterize generic rigidity. But a slightly different problem, which is 3D bodies, these are polyhedra, and they have bars connected between them. This we know how to solve in 3D and in any dimension. And so this is a picture of not only having, so their bodies, the bodies can spin, unlike vertices. Vertices can't rotate. Nothing happens when you rotate a vertex. Bodies have this extra degree of freedom. And so there are 2 things we're allowing here. One is to add a hinge between 2 bodies, and the other is to add bars connecting them from various random points. And it's generic, so these points will never coincide. And I think that's what makes this different from a vertex. Vertex bars always coincide. Here they all just attach to generic points. So it turns out you can simulate a hinge by 5 bars. They're equivalent. So both of these can be captured by 6k minus 6 property. Turns out these things will be generically rigid if and only if you satisfy the 6k minus 6 property and you have exactly 6k minus 6 bars. And this is proved by sort of 2 or 3 people. You need to add 2 results together, one from the 90s and one from much older, I think, in graph theory. But in particular, Tay was involved from 1984. And it's funny, the paper starts out with, you ask any structural engineer if you have 2 bodies, how many bars do you have to add to rigidify them? They will say 6. I'm like, okay, I didn't know that, but 6 is the right answer. And that's why the 6k minus 6, basically. And we can use this pebble algorithm to solve that. for free, basically. And this is actually implemented here in the same kind of software. I'll just run it quickly because there's a lot of pebbles. Every vertex has 6 pebbles. You just keep going. You need to cover every edge with how many pebbles? Before it was 4, so now it should be 7, I believe. One more than the 6 here, so 6k minus 6. Anyway, this graph, while it's not obvious, is minimally rigid in this world, and it corresponds exactly to the left example. It's hard to see because we've replaced the hinges here by 6 bars, so that's why we got all the duplicated edges. Here you see the duplicated edges are different from a rigidity standpoint because having 3 edges between the same pair of objects is no longer just the same as having 1 edge because they attach to different points. Each one can spin. These are universal joints, by the way. So these bars can rotate around the body can spin, lots of things can happen. But this is enough to rigidify it. Is there a question? Cool. Okay, I'm not going to prove that. You can read the papers if you're interested. But it's interesting. Bodies and bars are so much easier than other things. One other thing you can do is called angular rigidity. This is a fairly new result by the same people. If you have a bunch of lines in 3D and you have angular constraints, in this case, every triple of these lines has an angular constraint that it must be equal to alpha. That's what's drawn on the spherical picture. Over here, we have 2 bodies. So here we have lines, here we have bodies. And there are 3 constraints that fix the angles between these, how the angles meet at these bodies. And the claim is that both of these are angularly rigid, meaning things can still kind of slide up and down, but the angles are all fixed. And you can test this again. This case actually turns out it's the 2k minus 3 property, again, same as Lemon. This one, I've forgotten. I have to check. I think it's 3k minus 3. Yep, 3k minus 3. So, cool things. One last question. Connected bananas. So there was this 2 banana example, getting ahead of myself, which was kind of weird. You had this 1 banana on the left, 1 banana on the right, and there's this sort of implied hinge, as they call it, between the 2 points. The whole thing is flexible, but if you check it, it satisfies the Lemon condition. It satisfies 3k minus 6, which is what it should be for 3D rigidity. This is in 3D. Now this graph seems easy to figure out that this is flexible because there's a 2-cut. There are 2 vertices you can remove that disconnect the graph into 2 pieces. So if you could just subdivide, do the left part separately from the right part, you should be able to figure this out. Unfortunately, this example can be made more connected, and that's what the question was. So this is an old example by Henry Crapo. Modification by Walter Whiteley is that if you add a single point here and attach it to those 2 points, those 3 points, this will be 3 connected, still be flexible, and still satisfy Lemon. Because we added 3 edges in 1 vertex, so that still satisfies Lemon. So that kind of sucks. We think, oh, maybe 4 connected. Well, you can make it 4 connected too by adding a triangle in the center and connecting these 6 connections. Well, what about 5 connected? Well, 5 connected you can also do. And this is an example called the banana spider. Although it seems a bit of a misnomer, it should be, but I guess banana spiders are actual species. This really should be a banana insect because this guy has 6 legs, 3 on the left, 3 on the right. So there's an octahedron in the center, and then you add these 3 connections. And you can actually prove that any graph you have, any example that's maybe only 1 or 2 or 3 connected, whatever, you can make it 5 connected by whenever you have 2 4 connected components, or 5 connected components, I guess, just add a spider in the middle to bridge them, and it will be as flexible as before, and it will still satisfy Lemon. So 5 connectivity doesn't buy you anything, unfortunately. I guess you could ask for 6 connectivity, but 6 connectivity I think is impossible because you only have 3n minus 6 edges. So that's the limit. So sadly, connectivity is not the right, doesn't bias anything, and that's what we know about vertex and bar structures in 3D. Sadly, tough open problem. Any questions? All right, that's it for today.